For the first lab assignment in Physics 2211, we conducted an experiment to compare the movement of an object traveling at a constant speed, in my case a marker, with a theoretical model. To do this, I used the model and a physical principle of constant velocity so that I could theoretically predict the movement of the marker in terms of the distance from the origin with respect to time. And finally, I compared the results of the theoretical model with those obtained experimentally by measuring the trajectory of the marker, and I was able to conclude that the data relatively matches for both cases. In this experiment, we used two models to describe the marker's motion. The first one, the theoretical model, assumes a constant velocity where the object moves in a determinate direction with equal displacements over equal time intervals. Velocity is defined as displacement over time, and the position is predicted using the position update formula given by x final equals x initial plus velocity times delta time plus 1/2 of the net force over the mass times delta time squared. According to Newton's second law, when the net force is zero, momentum remains constant, ensuring constant velocity. So the experimental model, on the other hand, records the marker's position at different times as measured data points, and we then compare the two models, and this allows us to evaluate how well the theoretical predictions match the actual motion and identify deviations due to real-world factors such as friction or measurement errors. To define the initial conditions of the experiment, we identified the system as the marker and the table as the surroundings, assuming negligible friction between them. All measurements of displacement were recorded in centimeters using an online tracking tool. The marker was released to move along a straight line over a fixed period of time. And for the coordinate system, we oriented the x-axis so that right is positive. And since the marker moved from right to left, its displacement is relative to the origin r negative. These initial conditions allow us to consistently measure and analyze the motion of the marker in both the theoretical and experimental models. As we can see, the marker is moving from right to left, and after that, the distances were recorded every 0.04 seconds. Now, following the theoretical model, we coded a simulation to implement constant velocity motion. The initial velocity of the marker in the simulation was set equal to the average velocity measured from the experimental data, meaning that we use experimentally observed displacement over time to define a constant theoretical speed. In the code, we had a calculation loop such that each iteration represents a small time step defined by delta t, which we set equal to 0.041 seconds. The net force is set to 0 with fnet equals the vector 0, 0, 0, so that the velocity remains constant, though it's still updated using velocity equals velocity plus the net force over the mass times delta t. The position is also updated with the position equals position plus the velocity times delta t plus 1/2 of the net force over the mass times delta t squared. And since the net force is 0, this just simplifies to the final position equals the initial position plus the velocity times delta t. These updates allow the program to plot the marker's position and velocity versus time. Note that when we set the net force equal to 0 in the computational model, it means that the marker moves with constant velocity as predicted by Newton's second law. In real experiment, a zero net force does not imply that there are no forces acting on the marker, but rather that all the forces balance each other out. So for example, friction, air resistance, and any small pushes from the surface or the marker's release combine so that their vector sum is 0. So we cannot determine exactly how many individual forces are acting on their precise magnitudes, only that their total adds up to 0, resulting in no change to the marker's velocity. In analyzing the results, we found that the displacement values for the theoretical and the experimental models were very similar, showing that the constant velocity model approximates the marker's motion well. The theoretical model, however, predicted slightly larger displacements, and this discrepancy is likely due to some small amounts of friction, which slows the marker, and minor experimental errors such as timing inaccuracies or measurement limitations. And these factors explain why the experimental displacement is slightly less than the ideal predicted by the theoretical model. But what if we flipped the x-axis? So if we flipped the x-axis so that positive x and negative x were interchanged, the sign of all displacement values would reverse. However, the magnitudes of displacement, velocity, and the overall motion would remain the same, so the physical behavior of the marker does not change, only the direction relative to the coordinate system is reversed. So our results would therefore be something like this, but it's essentially the same. So in conclusion, in this experiment, the theoretical constant velocity model accurately predicted the marker's motion, consistent with Newton's second law. The experimental measurements matched the predictions, confirming approximately uniform motion, and some small differences with the theoretical model, showing slightly larger displacements are likely due to friction, air resistance, and minor measurement errors. And overall, the experiment validates the constant velocity model while illustrating minor real-world deviations from ideal behavior.